Hello everyone, today we're going to implement the trie, also known as Prefix Tree. It is useful in auto-completion and spell checking applications. First, if you're not familiar with what a trie is, basically a trie is a tree-like data structure. It starts from the root, and if you take a look at this path, cart, we have both the word cart and car stored in. We actually have to indicate whether a character is an end of a word or not, because it might just be a prefix of another word, but this word actually doesn't exist, so we have to indicate that. So if we remove that indicator, it means that this word doesn't exist. For another example, we have the word bits stored, but bit is not a word, though it's there, but it's just a prefix for bits, right? So yeah. So we are required to implement a constructor for the trie class, and an insert method and a search method which returns true or false, indicating an existence of a word or not. Also starts with checks for a prefix, but it actually doesn't have to be like an end of a word, right? So let's see how. Well, first let's look at the constraints. We have word and prefix consist only of lowercase characters. That means we don't have to use a hash map or something like that. We could just use an array or something like that. So we're going to have to implement a trie node class, which would have a boolean for indicating the end of a word, and a trie node, which is going to be an array of trie nodes indicating the children of this node, right? So first we have to declare a trie node class, right? So as we said, a boolean indicating an end of a word, and an array of trie nodes for the other nodes in the tree. Of size 26, because we're using only English, lowercase English letters, okay? After that, we would declare a root for our trie. Now we have to initialize this root for the constructor, right? So we would traverse the trie from the root. If the character we're trying to insert exists, we're going to go to the next character. If it doesn't, we would create it ourselves till we finish traversing the string, and then at the end we're gonna mark the last character as an end of a word. So yeah, trie node current is going to be equal root. That's where we start traversing from, and then we're going to traverse the string character by character. Right, so for the index we're looking for the character we're trying to insert, we would do it like that. Let me write it down and then I would explain it. So index equal word character at I minus a. So let me explain this real quick. So if the character we're trying to insert is an a, so it's going to be a minus a, so that means it's going to be inserted in the 0th index. If it's a b, then b minus a, that gives us 1, so it's going to be inserted in the 1st index, and so on. So yeah, and now we're going to check if the children of the current node have this character stored. If they don't, we would create that node ourselves now, right? So current.children of index equal null. That means we need to create that node. Current children of index equal new trie node. That means this character exists now, right? So after that, we would increment our current pointer, right? So yeah, current equal current to children at of index. So yeah, that's and also at the end we have to mark the current node as an end of a word. So current dot is word equals true, indicating that this is an end of a word, right? So for the search, we would traverse the trie from the root node, and we're going to traverse the string, and we're going to look for the character in the trie, right? So and at the end we're going to check whether this last character is an end of a word or not, right? So yeah, if we look here, we have to make sure that this last character is an end of a word, right? So trie node current equals root, and we're going to traverse the string character by character, as we said. And we're going to find the index the same way we did up there, pretty much like the same thing. And if that child, like in this index, if it doesn't exist, that means we can't find this word. We would just immediately return false, right? So current.children of index equal null. If it equals null, we just immediately return false. And after that, we would check if current is a word is true. We would just return that. If it's true, that means this word exists. Otherwise, this word doesn't exist. And now for the startsWith function, it's pretty much the same thing, other than the fact that we don't have to check if the current pointer at the end is an end of a word or not. We're just looking for prefixes. So we're just gonna start from the root and traverse the prefix string, right? And we're going to find the index the same way. Index equal word character word of character at I, right? Minus a, right? And if the current character, the children of the current character at this index doesn't exist, means that this prefix simply doesn't exist. So we would just immediately return null, right? Return false, I mean, yeah. And at the end of after the full loop, that means we can find this prefix, so we just return true, and we can run it. So in the search function, I actually forgot to increment the current pointer to point at the next child, right? And also in the startsWith, I also forgot to increment the current pointer. So yeah, that shall work now. Yeah, let's submit. Yeah. And now for the space and time complexity, for inserting a single word, it's gonna take big O of L for the time complexity and big O of L for the space complexity, right? That's for a single word. For searching and the prefix finder, it doesn't actually take any extra space, so it's just big O of L, right, for the prefix or the word we're looking for. But for inserting like many words, like inserting n words, actually we don't need to store all those characters. We would only be storing like the unique characters. So if you take a look here at car and cart, we only stored car once, so we're only storing the unique characters in the strings. So it's going to be big O of L for the processing and traversing, but big O of U, where U is the unique number of characters.